Hi, dear students. Welcome to Top Tutors, Toppers e-learning classes. Understand every single concept and be a topper. Today, we are discussing a new concept, that is nature of decimal expansion of rational and irrational numbers. Decimal expansion of rational number, decimal expansion of irrational number. In 10th standard Cbse textbook, it is coming under 1.5 section. The topic is given as revisiting rational numbers and their decimal expansion. So if you have a rational number, the standard form of rational number we can write in the form of P by Q, where P and Q are integers and Q not equal to 0. We are writing this decimal expansion. There are two types of decimal expansion really. First one is terminating decimal expansion. Terminating decimal expansion. It means the decimal expansion will stop after some numbers, can be 1, 2, 3, then stopped. So its decimal part is terminating, stopping, ending. Second is non-terminating. Non-terminating, it means not ending, right? Non-terminating, but recurring. Non-terminating, recurring means repeating, recurring, repeating. It means the same thing. Maybe if you write 3.5, then some digits or two digits are repeating, 3, 3, 3, 3, 3, 3, etc., etc. Goes on. This also can be written as 35.3 bar. Under the bar, which number we are giving? It is repeating continuously. Okay, it is non-terminating, non-recurring, but non-terminating, but recurring. Okay, this also some syllabus it will write like this. There's a dot on top. Different way we can write. It means this is repeating. So these are the two decimal expansion form nature of rational number. First one is terminating decimal expansion. Second one is non-terminating but repeating, recurring. Okay. If it is not rational number, it is not in the form of P by Q, where P and Q are integers and Q not equal to 0, then it is irrational number. Irrational number. This is rational number, normally denoted by Q. Q dash is irrational number. Irrational number, its decimal expansion will be non-terminating. Non-terminating means non-ending, not ending. And non-recurring. Non-recurring. So it is not ending, not repeating, right? Not repeating. So 35.10110110034 like that. So it is not ending, not repeating. Different numbers are coming. So these are the two type of numbers, rational and irrational number, and their decimal expansion. So these are the things what we are going to learn in details in this topic. Fine. So we can say that the decimal expansion of a rational number is either terminating or non-terminating recurring. So either terminating, can be terminating decimal expansion, otherwise non-terminating recurring, repeating. It converses a number whose decimal expansion is terminating or non-terminating recurring is a rational number. So if you can just see the decimal expansion, if it is terminating decimal expansion, we can say that that number is a rational number. If it is a non-terminating but recurring, repeating, then also we can say that that number is a rational number. Now the decimal expansion of an irrational number is non-terminating, non-recurring. That means not ending, not repeating. A number whose decimal expansion is non-terminating, non-recurring is an irrational number. Is a irrational number. All the rational and irrational number makes up the collection of real numbers. So real number we are denoting by capital R. So capital R means it is rational plus irrational. Set of rational real number is a collection of set of rational number and irrational number, right? Okay. Now we have some question. Write the following numbers in the rational form. That means P by Q form, where P and Q are integers and Q not equal to 0. We have given 4 numbers, 0.375. How will you change this decimal number into P by Q form? Numerator should be an integer. Denominator also should be an integer. So easy method, move this decimal to the end. So 1, we have to move from 1 to 3 digit to the right, correct? If you are moving 3 digit to the right means you are multiplying by 1000, correct? So that 375, it will change into 375 by multiplying this by 100 or even 1000. Multiply this by 1000 and divide. When you are doing something on numerator, you have to divide by, you have to do in the denominator also. So we can consider this as 0.375 by 1. So this also multiply by 1000. So it will change into 375 by 1000. So this is the rational form. What about this one? This one multiply by 1000 the numerator. Denominator also multiply by 1000. Because after decimal there are 3 digits. So it will change into 104 by 1000. This similarly, after decimal we have 1, 2, 3, 4 digits are there. So 4 zeros number 10,000 and denominator multiplied by 10,000. So 10,000 by 10,000 is 1. Multiplying by 1 will not change, right? Multiplicative identity. So this will change into 875 divided by 10,000. So putting 0 before nominator. Here after the decimal we have 1, 2, 3, 4 digit. So multiply the numerator by 10,000, denominator by 10,000. So you will get 233408 divided by 10,000. Fine. All these decimal numbers which are terminating, all these are terminating decimal numbers, right? When you are changing into rational number standard form, these are the answer we are getting. What the speciality you can see in the denominator? Anything? Fine. These decimals, I mean the denominators, it is the power of 10. Power of 10. So 1000 we can make it as 10 cube, right? This also 10 cube. This is 10 raised to 4, 10 raised to 4. We can write like this. So what is the speciality you can see here? What is the speciality you can see here? Any number with a terminating decimal can be written as the standard form of rational number, that is P by Q form, where P and Q are integers and the Q not equal to 0, q not equal to 0, or integers and q not equal to 0. But q as the power of 10, q as the power of 10. See, all these decimals, terminating decimal expansion, when we are making standard form of rational number, we can make the p by q form with denominator as the power of 10. Power of 10. All this you can see. See, here, everywhere, it is a power of 10. That's a speciality we can see here, right? Now, these numbers, that 375 by 10 raised to 3, we can simplify to their simplest form by taking away the common factors. So for that, we can prime factorize numerator and denominator, and the common factors we can take away. Fine. So you know how to prime factorize, right? 375, how will you prime factorize? 375. Common, we can take common. 7 plus 3 is 10, 10 plus 5 is 15. So 3 is it is divisible by 3. So divisibility rule, if you don't know, just check my video, divisibility rule. In detail, we have explaining all the divisibility rules from 2 to 12. So here one time, in 7, 2 times, carry over 1, 15, 5 times. 1 plus 2 is 3, 3 plus 5 is 8, not divisible by 3, so let us take 5. In 12, 2 times. 2 5s are 10, then 25, 5 times. Again, 5. How many times? 5 times. Again, we can put 5 one time. So 375 can be written as 3 times 3 into 5 raised to 3. 5 raised to 3. Similarly, this 10 raised to 3, how we can write? Let us prime factorize 10. Then how we can write? 2, 5 times. 5, 1 times. So 10 raised to 3, we can write it as, this 10 we have prime factorized. So you'll get 2 into 5 all raised to 3. So this we can write it as 2 raised to 3 into 5 raised to 3. Correct? So here 375 we can write it as 3 times 5 raised to 3, and denominator we have 2 raised to 3, 2 raised to 3, right? 2 raised to 3 into 5 raised to 3. Now 5 raised to 3 and 5 raised to 3 we can cut. So what is remaining? It will become equal to 3 by 2 raised to 3. Correct? Same way, all these numbers, 104 divided by 1000, 10 raised to 3, 875 divided by 10 raised to 4, then 2,33,408 divided by 10 raised to 4, to 33,408 international system. All when we are doing this way, what you will get? Let us see. We will get the numbers like this. Prime factorizing, this one we have already done, right? That we already done. 875 divided by 10 raised to 4. Here, 875, and we are prime factorizing, is not written here, 875 divisible by 5, right? In 8 1 times, 1 5s are 5, so there is a 3, then 37, 7 times, 7 5s are 35, so there is a remainder 2, then 25, 5 times. Again 5, how many times in 17? 3 times, 3 5s are 15, so remainder 2, 25, 5 times. Again 5, 7 times, then 7 1 time. So this 5 3 times. So here we have getting 5 3 times and 7 1 time. That is the numerator. And denominator also we have 2 raised to 4 into 5 raised to 4. Okay. So here 5 raised to 3 times and here 5 raised to 4. Okay. So this 5 raised to 3, and from here we can keep only 5, 1 5 we can keep, and this we can cancel. Okay. It means we are getting 7 pi 2 raised to 4 into 5. The simplest form what we have shown here. Similarly here 104, when you are prime factorizing, we will get 13 into 2 cube. 10 raised to 3 we can put it as 2 into 5 all raised to 3, that is 2 raised to 3 into 5 raised to 3. So 2 raised to 3 and 2 raised to 3 are common, so we'll get 13 by 5 raised to 3. When we are prime factorizing 233408, this is the prime factorization. So 2 1 2 3 4 5 6 times. So 2 raised to 6 into 1 7 times 521 is a prime number, 5, divided by 10 raised to 4. What we can do? 2 raised to 4 into 5 raised to 4. 2 raised to 4, and this cut how many times? So 2 raised to 2 will remain. That we have given here. 2 raised to 2 into 7 into 521 divided by 5 raised to 4. Okay. So we have both numerator and denominator, we brought it to the simplest form. We made it to co-primes. Both numerator and denominator have only 1 as the common factor, simplified to their simplest term. Now check the denominator. Can you observe any speciality in the denominators? Any speciality in the denominators? See, if you check the denominators, it appears that we have converted a real number whose decimal expansion terminates into a rational number of the form p by q, where p and q are co-primes. We made them into simplest form. And the prime factorization of the denominator, that is q, has only power of 2 or power of 5 or both. See, that is a speciality what we can observe. Here our denominator is 2 raised to 3. Here denominator 5 raised to 3. Here denominator 2 raised to 4 into 5 raised to 1. Here denominator 5 raised to 4. So what we have done? We have taken decimal number with terminating decimal expansion, that we converted into rational standard form. And the denominator we changed into the powers of 10. Then we prime factorized numerator and denominator and simplified. Then we can observe that some speciality on the denominators. The denominators have only 2 or only 5 or together both 2 and 5. Other than 2 and 5, there is no other prime numbers appearing in the denominator. That is a speciality that you can observe from this working. From this one, we can uh, give a theorem. Fine. So we should expect the denominator to look like this. For the reason, since power of 10 can only have powers of 2 and 5 as factors, fundamental theorem of arithmetic guarantees that, right? Now, rational number with terminating decimal expansion theorem. From this one, we can give some theorems. Rational number with the terminating decimal expansion theorem. What is it? Let x be a rational number whose decimal expansion terminates. Then we can express x in the form of p by q, where p and q are coprime, and p and q are integers, q not equal to 0. And the prime factorization of q, that is denominator, is of the form 2 raised to n into 5 raised to m. 2 raised to n into 5 raised to m, where n, m are non-negative integers. Powers are whole number. So there is only 2 or only 5 or both 2 and 5. If only 2 is there, then we can make it as 2 raised to n times 5 will become power 0. There is no 5, right? If only 5 means 2's power of 2 will become 0 and 5. That's yeah. If both are there, then 2 raised to n into 5 raised to m, or 2 raised to m 5 raised to n. Book we can interchange, depends upon the syllabus and books. Fine. So this is the theorem what we can say. Rational number with terminating decimal expansion theorem. So any rational number, if its decimal expansion is terminating, then if you are writing that number in standard rational number form, and if you prime factorize the denominator, it will contain only 2 or only 5 or both 2 and 5 only. Other than these 2 and 5, no other prime numbers will be there in the denominator. If it is there, then it is not a terminating decimal expansion rational number. It will be a rational number with non-terminating but recurring decimal expansion number. So this is the method how we can check the nature of the decimal expansion of a rational number. Clear? Fine. So converse of rational number with termination decimal expansion theorem, that let x equal to p by q be a rational number such that prime factorization of q is of the form 2 raised to n into 5 raised to m, where n, m are non-negative integers, means they are whole number. Then x has a decimal expansion which terminates. That's the converse we can say. Now, rational number with non-terminating decimal expansion theorem. Non-terminating decimal expansion theorem. Let x equal to p by q be a rational number such that prime factorization of q, that the decimal is not of the form 2 raised to n into 5 raised to m, where n, m are non-negative integers. Then x has a decimal expansion which is non-terminating but repeating, recurring. Non-terminating but recurring. That is the non-terminating decimal expansion theorem of rational number. So it's clear? Now, let us see one example. We have a rational number 1 by 7 because numerator and denominator are integers and denominator is not equal to 0. But denominator is a prime number 7 which is not 2 or 5. It is a different one. So by observing the nature of the denominator it doesn't contain 2, doesn't contain 5, right? It has a different 7. So it is not in the form of, not in the form of 2 raised to n times 5 raised to m. It is not in the form, not in the form of this one, correct? So we can say that this is a non-terminating, non-terminating but recurring number. Fine. So let us just divide 1 by 7 and see. So when we are dividing 1 by 7, we will get 142857. So here 3, here 30, here again we have 30, correct? So in 30, here see, here 30, we end up with 30 here, right? So this repetition will come again. From this part onwards, repetition will come again. So up to this one, we got 142857. Then again, we are getting 1. So we are bringing 0 down. In 10 1 times, 177, we got 30. See, here 30. So how many times in 30? 34 times. 4 sevens are 28. Then subtracting, you will get 2. I'm just bring these 2 here. Okay. Then we can put one more 0. 20. In 20, how many times? 7. 2 times. 2 sevens are 14. 20 minus 14 is 6. We can put one more 0. 60. In 60, how many times? 8 times, right? 8 sevens are 56. 60 minus 56 will be give you 4. You can put one more 0. In 45 times, 5 sevens are 35. Subtract 40 minus 35, you will get 5. You can put one more 0. In 57 times, 7 sevens are 49. Got 1. So this repetition will goes on. Repetition will go. It means it is non-terminating but recurring. What is the reason? Just by observing the nature of the denominator, we can say this rational number is, its decimal expansion is non-terminating, non-ending, but recurring, means repeat. Okay, so a rational number, by just observing, checking the denominator's prime factors nature, we can say that whether it has a terminating decimal expansion or non-terminating decimal expansion. Fine. Okay. So other than 2 and 5, any other prime factor is coming in the denominator, then it is coming under non-terminating decimal expansion, right? Non-terminating decimal expansion with recurring, repeating part. Clear? Clear, right? Fine. Now, so to determine the nature of the decimal expansion of rational number for the exam, when they are asking to check the nature, we have to follow these steps. I'll give you some steps. Always follow that steps for the examination. First, find coprimes. For that, divide both numerator and denominator by HCF. Bring them to the simplest form. Okay. Any common factors are there, divide it and bring the smallest form. That's compulsory. You have to do it first. Then prime factorize denominator. Prime factorize denominator. Or if you prime factorize numerator and denominator, then cancel. Then also it's possible. Okay. Prime factorize numerator and denominator, then cancels the common factors. Then check the denominator. If prime factors of denominator contains only 2 or only 5 or both 2 and 5, only, then it is a rational number with terminating decimal expansion. Terminating decimal expansion. If prime factors of denominator contains prime numbers other than 2 and 5, like 3, 7, 11, etc., it is a rational number with non-terminating but recurring, non-ending but repeating decimal expansion. In short, we can say that prime factors of Q will be either 2 or 5 or both if the decimal expansion is terminating. Otherwise, it is non-terminating, recurring. Clear? Got it, right? Fine. We'll do a problem. Check the nature of the decimal expansion of rational number 7 by 75. So what is the first step? Let's just simplify into their simplest term. If anything is common there in 7 and 75, we can simplify. Nothing is common, right? So just prime factorize 75. What is common in 75? We have 3. In 7, 2 times, 2 3s are 6, so remainder 1. In 15, 5 times. Then 25, 25, 5 times, again 5, 1. So 75 we can write it as 7 by 75, we can write it as 7 divided by, here we have 3 one time, and 5 how many times? 5 square. Nothing else, right? 1 no need to write. No mean. So see the denominator nature. What the denominator nature? The denominator contain 3 and 5, right? But it is not in the form of 2 raised to n times 5 raised to m, or 2 raised to m into 5 raised to n, 2 raised to m into 5 raised to n. Both way we can say. It is not in the form of 2 raised to m into 5 raised to n, because there is 3 also there, 3 also there. So it is not a number with terminating decimal expansion, but it is a rational number, right? It is a rational number. Numerator and denominators are integers. Denominator is not equal to 0, so it is a rational number. So what is the nature of decimal expansion? It is non-terminating, recurring, non-ending but repeating. Got it? Fine. So 7 by 75 we can write it as 7 by 3 into 5 raised to 2. So the denominator of rational number 7 by 75 cannot be written in the form of 2 raised to m into 5 raised to n. So it is not terminating, repeating decimal expansion. Clear? Okay. So this is the concept of this session. Make it thorough. Any doubts? You can ask me in the live class. Other students can WhatsApp me or email me anytime. Fine. So learn well. See you in the next class. Next class we will do the textbook problems of this section. Okay. Right. See you. Bye.